Christian, for the introduction, and many thanks for the organizers for the kind invitation. It's a great pleasure for me to be here. I'm enjoying very much the conference, and it's particularly a pleasure to present this result here because it was partially done when Fabio Cavalletti and me were visiting ESI in one of the conferences. So part of the work was done in one of the offices right there. Okay, so let's start with a warm-up on isoperimetric problem in the Riemannian signature. Okay, so it's a very old question, and it basically boils down to answer the following question. Given a space, what is the maximal amount of volume that can be enclosed by boundaries of a given area? Or more precisely, given a space, find the maximal function phi such that for any open domain, say with smooth boundary, it holds that the area of the boundary of S is bounded below by this function phi of the volume of the domain. Or equivalently, instead of maximizing the enclosed volume, you could say the dual problem is to minimize the boundary area. So amounts to say that given some volume V, solve the minimization problem. You want to minimize the area of boundaries which enclose some volume V. This problem is very classical. There is a huge literature. It goes back to the Greeks when the ambient space is Euclidean. You can find it in Virgil Aeneid, and it's called the Queen-Dido problem. And then there are many breakthroughs on the history. Let me just mention two that are among my favorites. One is the one of Steiner, who proved that in Euclidean space the minimizer is the ball, assuming that there is a minimizer, and for that he introduced the symmetrization that now bears his name. And then De Giorgi gave a full proof in the framework of a set of finite perimeter. And this is when the ambient space is Euclidean. Then there's a huge literature also in curved Riemann manifold. Let me just mention one of the most celebrated results, which is the diagram of isoperimetric inequality, which says that if you have a Riemann manifold with the Ricci bounded below by a positive constant, then the isoperimetry is at least as strong as in the sphere, round sphere, whose radius saturates this lower bound. But I could spend the whole seminar just listing beautiful results in the isoperimetric problem in Riemannian signature. So instead of doing that, the talk is what can we say about isoperimetry in Lorentzian signature. Okay? So let me just start with the warm-up on Lorentzian geometry. I will go quite quickly because we already had the seminar yesterday of Nicola where some of the notation was fixed. But to make you more confused, I will switch the notation. So for me, time is a minus. Okay. So for me, a Lorentzian manifold is a smooth manifold connected of dimension n+1. So the physical dimension is n+1 equal to 4. G, Lorentzian metric, is a symmetric, non-degenerate 0 to tensor with signature minus is the time and plus are the space directions. And for most of the talk, G is going to be smooth, and then in the very end, I will make some comments on non-smooth framework. So, given a Lorentzian manifold, given this G, we can divide the vectors depending on the value of G on them. So if GV is less than 0, then the vector is called timelike. If GV is 0, the vector is null. And if GV is less or equal than 0, is causal. And if GV is positive or V is equal to 0, the vector is said space-like. So to make a picture, so you say that at every point, I'm picturing the tangent space. You have a cone. This cone is where GV is equal to 0. It's called the null cone. Inside the cone, GV is negative. And these are the time-like vectors. And outside of the cone, you have space-like vectors. Okay. And analogously is for curves. So if you have a curve which is C1 or piecewise C1 or Lipschitz, you say that it is time-like if almost everywhere the tangent vector is time-like, and analogously for all the others. And then given a curve, say, of enough regularity, you can define the length of the curve just by integrating now the square root. Now, since g can be negative, you take the modulus of g gamma dot gamma dot. Okay. Now, since you want to have a future, not just now, since the time-like cone is two connected components, you have to say that one of the two is the future and and the other is the past. And for doing that in a compatible way, you assume that you have a continuous way of making this choice, and this amounts to say that there exists a continuous time-like vector t, which at every point tells you what is the future and what is the past. This is called a time orientation, and a spacetime is by definition a Lorentzian manifold with a time orientation. Okay? And we say that a vector v causal is future directed if is in the same quantity component of the time orientation, or otherwise is path directed. The same for curves. Then using that, one can define some causal relation. One say that the point Q is chronologically in the future of P if there exists a future-directed time-like curve from P to Q, and one defines the chronological future of P as I plus P, the point in M which are in the future of P, and one defines the causal future of a point P by saying that there is a future-directed causal curve from P to Q, or P is equal to Q, and the future and the causal future of P is denoted as J plus of P. Then there is in the Riemann setting, we have the distance function. In the Lorentzian setting, we have a replacement of it, which is called time separation function. And while in the Riemann setting, the distance function is the infimum of the length of curves, in the Lorentzian setting is the supremum of the length of causal curves, and that's because of the negative direction of the G. So the time separation between 2 points is the supremum of the length of curves, curves which are future directed, causal from P to Q, and we say sup also with 0. So if you have no causal curve, you just put 0, and you don't want minus infinity, just as notation here. And as a fact, while in the Riemann setting, the distance satisfies the channel inequality, in the Lorentzian setting, the time separation satisfies the reverse channel inequality. You don't have a metric space. Okay. Now, what about isoperimetry in the Lorentzian signature? So remember that in the Riemann setting, the isoperimetry problem is to minimize the area given volume. Okay? So if you find some, for some volume something with the boundary area 0, then the isoperimetry problem is trivial because it is 0, the minimum of the boundaries. And actually, in the isoperimetry, in the Lorentzian setting, this is what happened, because one can easily construct open sets of positive volume whose boundary is 0 area. So how you do that? So you take 2 points, take a point P and take a point Q, say Q in the future of P if you want. Take the past of Q and take the future of P. The boundary is going to be a null cone, is the union of 2 null cones. So on the boundary, the metric G degenerates, the area is equal to 0, and so you can find on Minkowski or any space for volume which is not too big, sets whose boundary is 0 area, but they have a positive volume. Okay, so actually, yeah. Yeah, the bound. Correct. Yeah, exactly. Take G, restrict to the and take the area form of that is 0. Exactly. That's what you would do in the Riemann setting. Yeah. Yeah. Correct. Correct. Yeah. Right. Okay. So then one could say, well, the isoperimetric problem is trivially solved, it is always 0, and I could finish here the talk. But actually, then you think twice and say, well, wait a moment, in the Riemannian setting, for instance, for the geodesics, what we were seeing is that the geodesics in the Riemannian setting minimize the length in the Riemannian setting, but they maximize the length in the Lorentzian setting. So maybe the right problem to look at in the Lorentzian setting is to maximize the area given the enclosed volume. And that's exactly, and that's what happens. Indeed, no. And in most cases it will be, but yeah, a priori, no. Okay, so instead of minimizing, the minimum problem is to maximize the area under some fixed volume constraint. So given V positive, we want to solve the maximization problem. So we want to maximize the boundary area of a set whose volume is V. Or equivalently, the dual problem is to find the minimal function phi such that for any open domain S, it holds that that you have an upper bound on the area in terms of the volume. Actually, why the bibliography in the Riemannian setting is huge, in the Lorentzian setting, the bibliography is much more limited. And in the next two slides, I will give you maybe, so to the best of my knowledge, an exhaustive list of what is known on the isoperimetric problem in Lorentzian signature. So the first result, to the best of my knowledge, is due to Ban and Eric in 1999, who studied the isoperimetric problem in flat Minkowski. And they proved the following result. Take a point in Minkowski, O, take its future cone, and take a subset, say S, in the future of this point. Then write take the cone that connects S to O by path-directed geodesics. Okay. Then what they can do is that they can estimate the area of S to the power n plus 1 with the dimensional constant, the volume of this cone. And the constant C is sharp, and they prove it via Minkowski. And Ban, in the same year, studied the isoperimetric problem in the Lorentzian setting in dimension 2 for Lorentzian surfaces with Gaussian curvature bounded from above, and he proved an isoperimetric bounds for regions of this form. So you have two geodesics, which are time-like, and they bound a simply connected region. Then more recently, Abedin, Corvino, Capita, and Wu generalized this result of Ban and Eric to warped product metrics. So the metric is warped product, and it has Ricci non-negative in the time-like directions. So it's more general, but still in a warped product framework. Then Lambert and Scheuer in 2021 gave an isoperimetric bound, again in warped product spaces, and now assuming that the Ricci is non-negative now on null vectors. This is called null energy condition, and their proof is via Minkowski flow. And then that's all, to the best of my knowledge. And let me stress that you have either a strong assumption on the space, so it is either the space is always a warped product, or it is of dimension 2. So the another question is, what about higher dimensional spaces without symmetries? Can one prove any area bound, any isoperimetric type inequality? Okay, so in order to our contribution in this direction, let me introduce some basic notation. So given Mg a space-time, so a time-oriented Lorentzian manifold, recall that a hypersurface V is called the Cauchy hypersurface if it is met exactly once by every inextendible future-directed causal curve. This is a fundamental notion in general relativity. Indeed, Cauchy hypersurfaces are good initial conditions in order to study the evolution of the Einstein equations, and by the celebrated result of Choquet-Bruhat. And if you don't know, if you've never heard the global hyperbolicity, you can take as definition of global hyperbolicity the fact that there exists a Cauchy hypersurface. Otherwise, if you are familiar of the notion of global hyperbolicity as no closed causal curves and compactness of causal diamonds, well, this is equivalent to that. Okay? So, well-known studied notion of basically local compactness of space. Okay. Okay. Now, given V a Cauchy hypersurface in M, a subset S in the future of this Cauchy hypersurface is said to be a graph over V if for every point in this subset, for every geodesic which relies the Lorentzian distance from this point to the original set V, this point is the unique point of intersection of the subset with support of gamma. It's a bit cumbersome way, but is the precise way of saying the following. So you have V, here you have S. You want that when you take the time separation from V, you have a unique point of intersection, and you don't want something like that. Okay? So if you have a geodesic which does that, you have more than one point of intersection, so that's not a graph. Okay? Okay, and just an easy lemma is that if both V and S are Cauchy hypersurfaces, and S is in the future of V, then S is a graph over V. That's because you have just one point of intersection. Okay, good. Now, given a Cauchy hypersurface, I want to define basically its Lorentzian distance from it. We call it time separation from this surface. It is defined in the usual way. So take any point y in the future of V, and then the time separation from V is the sup among all the points in X of tau xy. Is what you do in the reference setting for defining the distance. You would put an inf here. Okay? And then we define the distance between V and S, so S is in the future of V, as the infimum of this tau V. So it's a min-max quantity. Okay, and then last piece of notation, we are interested, given V and S, given, so here we have V, here we have a Cauchy S, they are both Cauchy hypersurfaces, and then we are interested in the region which is between them. And a way to describe it is to say is the region spanned by geodesics from V to S which realize the time separation. Basically, what I want to say is the open region whose boundary is given by V and S. That's what I have in mind. That's prevented by global hyperbolicity. Yeah. Okay, and then that's all the notation, and we can get the following statement, which is joint work with Fabio Cavalletti. Okay, so let M be a globally hyperbolic spacetime with non-negative Ricci on time-like directions. This is a well-known assumption in general relativity, which goes under the name of Hawking-Penrose strong energy condition. Okay? And take two Cauchy hypersurfaces, V and S. S is in the future of V. Then you can bound the area of S times the distance between V and S with n plus 1 times the volume of the region between V and S. Okay? So, a couple of comments. So, to the best of my knowledge is the first Lorentzian isoperimetric-type inequality with no symmetry assumption. So here we have no symmetry assumption on the space, only a lower bound on the Ricci. And the inequality is sharp. So this constant is sharp in the sense that equality is attained asymptotically for the following example. So take a Lorentzian cone over Sn. Okay, so here you have Sn. Sorry. Such that this is the identity. This is the negative direction. This is going to be singular here, but I don't care. Let me just stop everything here at some epsilon. This is epsilon. Okay. So now, if you take as a region, take this one as V epsilon, is this slice at epsilon, and as S, take this one, slice at t equal to 1. Okay? And you can check that they are both Cauchy hypersurfaces for this Lorentzian cone. And then, just in this computation, is that the distance tends to 1, and the volume tends to 1 over n plus 1 times the area. So you cannot put a better constant, because otherwise you would violate by taking epsilon small. Okay? And actually, I'm doing this because I want a smooth space, but actually, we prove the result in a non-smooth setting, and then you would allow really the cone. So the cone really achieves the equality if you state this in. Yeah, sure. Don't. Yeah, we don't need it. Yeah, it is just for simplicity of stating. But exactly. So what we just need, it's a very good point. So what we just need is that they are achronal. So what we don't want is that you have a curve which is say time-like and start from the surface and goes back to a surface, and that's it. Just achronal. So we need that they are both achronal and that they are one on top of the other in a way that when you take geodesics which maximize the time separation from one, you hit the other one. And if they are both Cauchy, that's automatic, otherwise it's an assumption. Correct, yeah. Very good. Yeah. No, I don't. But for globally hyperbolic spacetime, tau is continuous. Okay, no. If V Cauchy, okay, but if V is not Cauchy, you need you need also that V is future time-like complete. Okay, so now let me give a formal sketch, which is at the backbone of the real proof, which contains basically the basic geometric ideas, but I will skip all the technical details. Okay. So the geometric idea is the following. So we have our surface V, and then we have S in the future V. Now, for every point alpha in V, consider x alpha, which is the integral line of minus the gradient of the time separation from V. Okay? So here you have alpha, and then you have your x alpha. And you do this for every point alpha in V. Now, since this surface S is a graph over V, for every x alpha, we have a unique point of intersection between this ray and S. Okay? And let's call B alpha the value of the parameter along the geodesic, which is parameterized finely, which realize this point of intersection. Now, since by definition of the distance between V and S, every B alpha is bigger or equal than the distance between V and S, because the distance between V and S is the infimum among all these B alpha. Okay, now by construction, it's not too hard to see that the second surface, S, is the union of the endpoints of this geodesics. So for every point in S, we have a ray which arrives here. And the region between V and S is the union of these rays. That's by construction of how we define the CVS. And actually, these unions are both disjoint up to a set of measure 0. Okay, now since you have a good partition, then you can do this integration of the measure that, if you have never heard about it, is kind of a non-straight Fubini theorem. So think that if you are in the square, then you have, say, the square in R2, then you have the partition into vertical segments, and then you can write the L2 measure with Fubini here you have a partition which is not as straight, but you can still write a B-type integral like this. So the volume of this region between V and S can be written as an integral first on V, and then second an integral on this one-dimensional segment x alpha, and now with some weight, since you don't have a straight integration. And then at first approximation, you can think that the area of S is equal to the integral of this weight evaluated at the endpoints. That's not exactly true, but you have just an inequality, which is what you need. So the area of S is bounded above by the integral over V of these densities at the endpoint. Just a small remark for the people who know this integration technique. In the Riemann signature, or in the metric setting, one has bigger or equal here. And that's because of triangular inequality, while in the Lorentzian signature, we have less or equal because of the reverse triangular inequality. Okay? Now, the key step is to transfer the curvature information from M, from the ambient space M, to these rays. Actually, what happens is that each one of these rays, x alpha, with the Euclidean distance and with this weighted measure, verifies the Lochstern-Villani CD0 n+1 condition, which is an overkill to say that the density to the power 1 over n is concave. Okay? Now, what does it mean that the density is concave? Then we have a monotonicity of the slopes of the chords. So we have that h alpha at time t over t to the dn is monotone non-increasing. And integrating, so it is monotone increasing, means that it has the minimum at the last point, which is b alpha. So h alpha t over t to the n is bigger or equal than h alpha b alpha over b alpha to the n. So I just bring t to the n here and I integrate. Now this is a piece of cake, and we get this. Then we can, putting all together, we have that the volume of the region between V and S can be written with this integration in this way. Now, for each integral from 0 to b alpha, we have this lower bound, so like it here. Now, for every alpha, b alpha is bigger or equal than the distance between V and S. So this goes out. And now, what about the integral of these endpoints? Well, this is bounded below by the area. And so this gives the isoperimetric inequality. Okay? So of course, then writing a full proof takes several pages, but this is the geometric argument at the backbone of the real proof. Okay. So now I'd like to discuss a couple of applications of this inequality. The first one is a bound on the area of Cauchy surfaces inside the black holes. So two celebrated examples of black holes are Schwarzschild and Kerr metrics. So they model vacuum spacetime containing a static in the case of Schwarzschild and a rotating black hole in the case of Kerr. They both solve the vacuum Einstein equation, Ricci equal to 0. So in particular, they have time like Ricci, which is non-negative. And one can build also several other examples of black holes satisfying the strong energy condition. For instance, there's a paper of Dafermos, Olzegel, and Rodiansky with construction of several black hole metrics. And typically, by the Penrose censorship conjectures, a black hole has some properties, which are the following. So one usually has that a black hole solution contains a closed null hypersurface called the event horizon, which has the following two properties. The horizon divides the spacetime into two globally hyperbolic regions, the interior and exterior of the black hole. Let's call B the interior. And then in the interior of the black hole, there exists a subset, sigma, which is called the center of the black hole, which it is conjecturally singular in the Penrose conjecture, but we don't need it to be singular. What we just need is that all the inextendable time-like curves in B end in finite time falling into sigma. So basically, is saying that if you are inside the event horizon, you have no chance but falling into the center of the black hole. Okay, then with the same proof of the result before, with Fabio we can prove the following statement, which is the following. So consider the interior of a black hole which satisfies the strong energy condition and the cosmic conjecture, as stated above. Let sigma to be the center of the black hole, and S to be any Cauchy surface for B, for the interior of the black hole. Then the distance between this Cauchy surface S and the center of the black hole, sigma, times the area of the Cauchy surface is less or equal than n+1 times the volume of the black hole. What is the physical interpretation? Okay, so a Cauchy surface S should be thought of as the universe inside the black hole at a given time. So basically, if you are unlucky enough to be inside the event horizon of the black hole, you look around you, you look at the universe that you can see around you, and at a given time, this is S. So this area of S is the three-dimensional volume that you can see around you when you are inside a black hole. Then, what is this distance between S and sigma? Well, that's the maximal lifespan for an observer before crashing into sigma. So basically, it's the life that you can live when you are there, before crashing into the center. So this is saying that your maximal life expectancy times the three-dimensional volume that you are seeing is bounded above by the volume of the black hole. Okay, a second, say, interpretation of this area bounds is in cosmological spacetimes. So cosmological spacetimes are particular solutions of the Einstein equations which are used by cosmologists to model the universe from the Big Bang up to now. So basically is you look at the universe at a very, very large scale and you want to get some information there. So the model is that your four-dimensional space-time is topologically a Lorentzian cone over some three-dimensional manifold sigma. Let's put coordinates t time and x in sigma. And t equal to 0 is the origin of the universe, is the tip of the cone, correspond to the Big Bang. And now, if you choose in our bound as Cauchy surface V equal t equal to 0, so the origin, the tip of the cone, that's non-smooth, but what we just need is that all the curves start from there. So since it is the Big Bang, everything starts from there. And then take S to be any Cauchy hypersurface. One can adapt the proof that I discussed above and prove the same statement. And now what is the physical interpretation of this statement is that, well, the quantity distant from V to S is nothing but the age of this three-dimensional slice, S. And moreover, the cone from V to S is nothing but the time-like past of this Cauchy surface S. So what you get is that the three-dimensional volume, Riemannian volume of this Cauchy surface S times the age of this surface, or sometimes the age of this slice, is bounded above by n+1 times the volume of the past of this. Actually, I gave the statement for non-negative Ricci, but actually we prove a more general statement with any lower bound on the Ricci, but then you are not going to have such a neat statement. You're going to have some function with positive k, which will depend, it will involve trigonometric function. For negative k, it will involve hyperbolic trigonometric functions of the various terms. But the good thing is that we can handle any cosmological constant. Now, there is a, so how to relate this with previous literature. So there is an isoperimetric inequality for Cauchy hypersurfaces in Friedman-Lemaitre Robertson-Walker spacetimes by Abedin, Corvino, Capita, and Wu in 29, assuming non-negative time like Ricci. And what they assume is that the slices t equal to constant have constant sectional curvature, so that they are space forms. So this is this means that every time slice is homogeneous and isotropic. This used to be the setting for cosmologists, this Friedman-Lemaitre properties of working spacetime, because at a good degree of approximation, the universe at very big scale has this property. But some recent observation, it's quite funny that it's a report of last year from the European Space Agency, detected some anomalies in the cosmic microwave background and challenged this model. So the fact that, they say that at first approximation, it is a good model to assume that the time slices have constant sectional curvature, but at a better level of approximation, not so much. So it is good to have a result which doesn't have this assumption, and say our techniques allow to handle also cosmological spacetimes which are not isotropic and with any cosmological constant. Okay, right. So this was about the isoperimetric problem, but let me end by discussing the bigger picture. So what's the longer-term goal? So this isoperimetric model that I presented today, I presented it for simplicity for spacetimes which are smooth and for non-negative time like Ricci. But actually, in the paper with Cavalletti, we proved a more general result for non-smooth Lorentzian length spaces and with any lower bound on the Ricci. So we just think that the time like Ricci is bounded below by some constant k. So what is this context of non-smooth Lorentzian spaces? You will hear more in the next talk by Clemens, but let me do like in cycling that tira volata. So Clemens will do the sprint in the next talk. So, but a small introduction. So these Lorentzian length spaces were introduced by Kunzinger and Seemann in 2017 after work of Kramer and Penrose in the 60s on causal spaces. And these are Lorentzian counterpart of metric spaces. So basically, a Lorentzian length space shall be seen as a non-smooth Lorentzian manifold in the same way as a metric space shall be seen as a non-smooth Riemannian manifold. And McCann and myself and Sur independently characterized the time-like Ricci lower bounds and the Einstein equation for smooth spacetimes using optimal transport. And the good thing is that this characterization makes sense also in the non-smooth setting of Lorentzian length spaces. So with Fabio, we studied Lorentzian length spaces with the time-like Ricci lower bounds that are called time-like CDKN. So the CDKN is the Losch-Thurm-Villani CDKN. Now we put a T because we are interested in the time-like Ricci bound. And we studied some properties of the spaces like Lorentzian Bishop-Gromov, stability under convergence, and the synthetic version of the Hawking singularity theorem, which basically says, which has this kind of interpretation. So in the, what are the singularity theorems? They, in a nutshell, they say that under some geometric assumption on the space, one can build some inextendable time-like curve, and then the fact that this curve stop leaving, it is interpreted as a singularity. Now, is a kind of a weak way of saying it is singular because a priori you could extend the space and extend the curve itself. So in the classical statements of the singularity theorems by Hawking, Penrose, and various variants, the space is assumed to be smooth or C2, say. Then there's been a huge work by the Austrian school, which is very remarkable, of lowering the regularity of the metric to C11, some results go to C1. And actually, with the paper with Fabio, we can go even below. So we can basically say that no matter how low you go in the regularity of the extension, as long as the extension has some energy condition, like the strong energy condition of Hawking-Penrose, you cannot extend the space and avoid the singularity, assuming that the extension has the non-negative Ricci in the time direction in the synthetic sense. Okay, good. Then there is some more work by Brown recently, Then there is a characterization of the synthetic null energy condition by McCann and Ketterer. And then there is some recent work by Brown and McCann about variable time-like Ricci lower bounds and application to similar theorems. This is more recent results. Now, what is the broad goal of this line of research? So basically, is the following. So optimal transport is revealed to be a very effective tool for studying spaces with extremely low regularity in the Riemannian signature. So more precisely, one can use optimal transport to define and study metric measure spaces with reach bounded below by k and the measure bounded above by n. In aesthetic sense, and this is the celebrated theory of CDKN spaces of Losch-Thurn-Villain. Now, inspired by the success of this theory of metric measure spaces as find the CDKN condition, we aim to develop optimal transport tools in low regularity Lorentzian setting and build a synthetic theory of Ricci bounds in Lorentzian signature. Okay? What is the theory motivation of studying spaces of low regularity in the Lorentzian setting? Well, non-smooth Lorentzian metric and singular Lorentzian spacetimes are kind of ubiquitous in general relativity. For instance, when you study the evolution of Einstein equations, often you study that in Sobolev spaces, so which are not smooth metric, they are Sobolev metrics, or in several models, like when you model inside or outside of a star. If you model black hole singularities, implied gravitational waves, some approaches to quantum gravity, these are all settings where you have to work with non-smooth metrics. And in quantum gravity, maybe you don't even have an underlying smooth manifold. And why, so this is why non-smooth, and then why Ricci curvature? Well, because the Einstein equations are written in terms of Ricci curvature. So the Einstein equation in the vacuum are Ricci equal to 0. So far, what has been the approach? So there's been basically two approaches. One is the one, say, of Penrose and Hawking, which is to work geometrically on the complement of the singular set. So just using classical tools of differential geometry and global differential geometry, and this gave beautiful results and these singularity theorems. Or there is an analytic approach to work with Sobolev Lorentzian metrics and analyze the Einstein equation as a nonlinear hyperbolic system of PDEs. So what we are proposing, not just me, but as a group of people that are working in this direction, is a novel point of view, which is to provide a synthetic geometric framework for studying singular Lorentzian spaces, their curvature and their geometric properties, including the singular set. So we don't want to take out the singular set, we want to include the singular set and provide tools for studying the space with singularities. Why? Well, because in the universe you have plenty of black holes. So you don't take, often what one does is take just one black hole, take out the center of the black hole, and then everything is smooth. But in the universe you have plenty of black holes, you have plenty of planets, you have plenty of gravitational waves. So if you start taking out singular things, you could take out many things. So it's better to, it could be useful to provide tools to include the singular set. So we have some, we have a kind of a background for studying that. We have some initial results which are encouraging, and then just the future can say if this program will be successful. So thank you for your attention. Okay, I think yes. So in Minkowski, let's recall what is the statement. So you have you take a point, O, you take a surface S here, and then you take the past. Okay, and then you can bound the area of this with the volume. So you have equality if and only if it's a cone and this is flat. Yeah. Basically it's the same. So what we can say is that if you have equality, in the in here, then you must be a cone. So you have equality here if and only if your space is a cone, your V is the tip of the cone. Okay, so basically, so actually here I stated it for smooth. So in the smooth category, you don't have rigidity, you have just sharpness. That's why I just talk about sharpness, because I didn't want to enter into the non-smooth setting. But if you ask for the rigidity, then you have to enter in the non-smooth setting, and you have equality if and only if you are a cone. And S must be, yeah, so is a cone, and S is equal to T equal to a constant. T equal to a constant in the cone, yeah. So what we do is okay. We say, yeah, the statement is okay. We say that the region CVS is smooth. So the statement seems okay. If you are completely non-smooth, then you have just volume cone. Since we wanted to have a stronger statement, what we assume is that this region CVS, the interior one, is smooth. The singularity can just happen in S. Then since you're smooth, then from the volume rigidity, you get the real rigidity. So then you are rigid. It's a good question. We haven't thought yet. Probably it will be true that varying the volume, you will have some, with the lower bound of Ricci, you will get some concavity. But we haven't thought, but it's a good question. All right, this is a good question. Not with this, I think so, but not with these techniques. I thought about it. No, with k different than 0, you get exactly the same thing. So you get area less or equal, then instead of, you have to bring the distance here, and then you get a function which depends, which involves, say, k positive sine of some combination of volume and distance. It is something which is explicit, but just a bit ugly. And it's again sharp because then it is achieved in de Sitter for positive k and then de Sitter in negative k. It's ugly, but it's what it is. Thank you.